Okay, so last couple days we've been talking about universal gravitation and we've been talking about satellite motion. All right. Last thing we're going to talk about is gravitational field strength. And gravitational field strength is very closely related to gravitational attractive force. Okay? But instead of the force attracting two objects together, gravitational field strength is the rate at which they move together. In other words, the gravitational acceleration between the two rather than the force of gravity between the two. Okay? So essentially, gravitational field strength is gravitational acceleration. Okay? This allows me to calculate little g for any point in relation to the central body. All right? So if I did this for Earth and I was standing on the Earth's surface, what would I get for gravitational field strength? 9.81 meters per second squared. Okay? That's the Earth's gravitational field strength when you're standing on its surface, and then it decreases exponentially with distance from there. Okay? All right. So gravity is a field. That means it can exert force without being in physical contact with something else, just like electricity and magnetism. Okay? And gravitational field strength is numerically equal to acceleration due to gravity at any given point. So if a question asks, calculate the gravitational field strength, you are looking for little g. Here's how we figure that out. It's actually pretty straightforward. Okay? Could I say this and be right? I sure hope so. That's like saying 1 equals 1. Okay? I should be right about that. Okay? Are there two ways to do that? Those two things should be equal. Agreed? Okay? Now, if I set these two things equal to each other, okay, this would be mass 2, the smaller of the two masses. Okay? Because whenever we're calculating the weight of something, we don't use the mass of the Earth when we do that. Is everyone okay with that? Okay. So what happens to mass 2?
It cancels.
It cancels. There's how you calculate gravitational field strength. You just cancel mass 2. Because all things fall at the same rate, 9.81 on Earth, regardless of their mass. Okay? So calculating gravitational acceleration is really just setting gravity equal to gravity and canceling the small mass. Okay? Because that gravitational acceleration is due to essentially the larger mass. All right, so is that going to be a pretty easy formula to use? Okay. And you're never going to have to set this equal to anything else. It's not like the satellite questions where we set big FG equal to FC and then had to do a bunch of manipulating. You're only ever going to use this formula to solve stuff within it. Okay, it's never going to be set equal to anything else. The thing to watch for is when you get a question that is actually asking for gravitational field strength. The most common mistake I see is when a question says, calculate the gravitational field strength, or here is the gravitational field strength, people use the force of gravity formula instead. Okay? If the question is saying, what's the force of gravity, okay, or what's the gravitational attractive force, then it's saying find F. If it's asking for field strength, it's looking for little g. Okay? Just have to understand that they are two different things. What I see most often is people confuse the two. Field strength is the attraction rate between them. Okay? The force of attraction is how hard they're pulled together, not how fast they're pulled together. Okay? All right. So, Earth and Moon both have gravitational fields. Would you agree? Do they overlap? Does the Earth's gravitational field and the Moon's gravitational field overlap? Okay? What evidence do we have of that? Tides. Okay. If we were not inside the Moon's gravitational sphere of influence, there would be no tides. Okay? So it's important that we understand that, yes, in fact, there is a overlap of those two gravitational fields. Okay, so Michael Faraday was actually the guy that came up with this idea of the field. Okay? That a gravitational field means you have an area of influence and there are no magic strings or fluids or whatever else people would make up that connected objects. There's not these invisible wires running through the universe connecting everything together. Okay? So his idea was that anything could exert an attractive influence, okay, over a certain area depending on the strength or the mass of that object. Okay? So obviously Earth's gravitational field is larger than the moon's. Okay, but only as long as you are closer to the Earth than the moon. If you get too close, if you get closer to the moon, what will happen to the gravitational field? It'll switch. Okay, you'll start being attracted to the moon because you're closer to it. Okay, so that was something that like NASA had to think about when they were sending people to the moon for the first time. Okay, Earth's gravitational field isn't as simple as this diagram. Okay? In this diagram, it says that if you have a gravitational field, your field strength decreases as you move away, so the length of the arrows gets smaller, okay? But they all still point directly towards what? The Earth's center. Now, there's another body, though, nearby the Earth, the moon, which throws off the direction a lot of these arrows point and the length of a lot of these arrows. So you bring the moon into play, and suddenly that field changes. Okay? And there's actually a balance point right here where you would be equally attracted or neutrally attracted. Okay? You could just sit there. There would be no attractive force net in either direction, and thus no acceleration or field strength in either direction. Okay? So when NASA was plotting how they would get to the moon, they had to take into account that the force of the engines and the force of Earth's gravity were not the only things that needed to be accounted for. Okay? When they got to a certain point, the spacecraft was going to accelerate towards the moon of its own accord, okay? Not because of anything they were doing. Okay? Everyone all right with that idea? Yeah. Okay. All right, so we can picture that obviously gravitational field strength, okay, because of this formula, okay, decreases exponentially as we move further away. As we separate the centers of the two objects, the rate of attraction will exponentially decrease. Okay. All right, so could we calculate then pretty simply what this number should be for Earth? Do we already know what it should be? Okay. On our formula sheet it says average acceleration due to gravity, 9.81. So it isn't 9.81 everywhere. Right? So let's use Earth's average radius, okay, which is on our formula sheet, not the value they're going to give, okay, and see if we can calculate what little g will be. So we'll have 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 24, and then divide that by 6.37 times 10 to the 6 squared. Okay, that should give me the acceleration due to gravity on the surface of the Earth. .83. Pretty close. Okay. That's using the Earth's average radius, not the Earth's equatorial radius. Okay, so we're getting 9.83 meters per second squared. This is a fairly accurate way to do that, especially given that we've probably rounded off the Earth's mass and Earth's radius significantly. All right, using the information on here, calculate what the acceleration due to gravity would be on the moon. going to change the radius of Earth to radius of the moon, and mass of the Earth to mass of the moon. Okay? Alright, so we'll have mass of the moon, 7.35 times 10 to the 22, that's their number. Okay, 1.74 times 10 to the 6, okay, for the radius of the moon. Okay, so I think I'll just change some of those numbers in the entry. Alright, so 7.35, 22, okay, and then 1.74. All right, so I get 1.62 meters per second squared, or also newtons per kilogram are also acceptable units. And if you divide newtons by kilograms, you also get meters per second squared. Okay, either one of those is fine. All right, so is the acceleration due to gravity on the moon significantly less? Yeah, 1/6 of what it is here. All right, everybody okay with how those gravitational field strength calculations go? Okay, got a couple of videos to show you, and then we're going to work on a few gravitational field strength problems to kind of end off the day here. Okay, so the videos I'm going to show you have to do with like the movement of Earth and the moon. Okay, the movement of Earth in its orbit. So some of Kepler's laws, things. So celestial mechanics are strange. Okay, there's lots of things we have to take into account. Okay, it's more than just the Earth goes around the sun. Okay. All right, so I would like you guys to try a few gravitational field strength questions. Okay, I would like you to try 2 and 3 here. Okay, so try questions 2 and 3, and we'll talk about those in a minute. Okay, so for number 2, okay, we have an 80 kilogram astronaut in orbit. They are 3.20 times 10 to the 4 kilometers, which makes them 3.20 times 10 to the 7 meters, okay, from the Earth's center. Calculate the gravitational field strength at that position. Okay, well, gravitational field strength is big G times the mass of the Earth over R squared. Do I even need to know that the astronaut is 80 kilograms for this? Not at all, okay? His mass is irrelevant. Right. So 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 24, okay, divided by the radius they gave us, 3.20 times 10 to the 7 squared, okay, will give us the acceleration due to gravity or gravitational field strength at that position. Okay, 5.98. 24, okay, and then divide that by 3.20 times 10 to the 7 squared. Okay, so does he experience very much gravitational acceleration at that distance? No, but that makes sense. You're exponentially less attracted to the Earth the farther away you go, so you should move towards it exponentially less as quickly, okay, the further away you get. All right, now for part B, it says, what would the magnitude of the gravitational field strength if they were orbiting the moon at the same distance? I only need to change one number in there. What is it?
The mass.
Yeah, I just need to change it to the mass of the moon. Okay, so I can just hit second entry, okay, go back here and change this to 7.36 times 10 to the 22. Okay, said the same distance. Wow, I'm hardly attracted to the moon at all. Okay, the rate of attraction there is virtually 0. Okay, all right, how many people have done number 3? Okay, I'm going to give you a few minutes on number 3. It shouldn't take that long, okay, simply because you don't have to do any algebra. All right, so I'm going to give you a couple of minutes on 3, and then we're going to talk about it. What are they asking for in number 3? Field strength or force? Force. This is one of those questions. This is why I have you do this. You need to read questions carefully. Okay? In this question it says, what would be the gravitational force on a 70 kilogram person? not the gravitational field strength at whatever point they're talking about. Okay, this time they want Fg. Okay, you see the word force, you're looking for Fg. You see the word field strength, you're just looking for little g. Okay, now here's what happens. On the unit exam, every semester, I put on a question and it has to do with gravitational field strength, and I boldface, italicize, and underline the words gravitational field strength. And 1/3 of you will solve it as a force question. Okay, so prove me wrong. I want to be wrong about this thing. I've been wrong once. I've had one class who proved me wrong. Okay? 1/3 will not read the question carefully enough and will solve it the wrong way. Okay? Prove me wrong, please. I desperately want to be wrong. I'm used to being wrong, but like I want to be wrong about this. Okay? All right, so on this one here, I'm doing this. Big G times the mass of the Earth times the mass of the person, okay, divided by r squared. And r is going to be 6.6 times the Earth's radius. So all I have to do is plug in numbers here. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 70 kilograms. Okay, divided by 6.6 times 6.37 times 10 to the 6 squared. Okay, when we do all of that, okay, in our calculator, so okay, so the gravitational attractive force there would be 16 newtons. All right. Okay, tomorrow we'll probably spend a little bit of time. How are we feeling about this stuff? Do we need to spend any more time on this? A little bit more? Okay. Then we'll spend a little bit more time looking at kind of the second half of the unit here, the gravitation stuff, all of it. Okay. Thursday we'll do the assignment on gravitation. Friday we'll do a unit exam review of Unit 3. Okay, that is where we are at right now, guys.